Welcome again to the NPTEL course on storage systems. In the previous class, we looked at how to manage a system with multiple types of storage. Right? We discussed this 5-minute rule, and then we tried to see how you should balance capacity versus the number of I/O operations per second you need, right? So, we will continue a bit on discussing the types of storage systems that are there, okay? So, in the beginning, just as an illustration, we looked at memory stick, and in the memory stick what really goes on, right? We had a brief look at that particular thing, okay? Today, we will start looking at again in all the types of storage that are available, okay? And I think first of all you should know that storage is everywhere, right? You can use it in mobile storage. For example, it's there in memory stick, camera, smartphone, laptop also, right? Nowadays you can get laptops with SSD only, okay? So they're expensive, but they're lighter, and they are also somewhat better with respect to, if you drop it, most likely the laptop will still live, okay? Of course, even disks can be designed so that if you drop them, they survive. How do they do it? They do it by, they have some kind of standard accelerometers, and then it finds out that it is dropping, and therefore it can park the head, okay? Normally what happens is that there is a head, and which if it crashes into the medium, then you lose it. So the thing would be to, as it is falling, detect that it is falling, and then park it safely in a place, so if it falls, the head doesn't hit the medium, okay? So that's the idea, okay? So many laptops also have that feature. So if you have that feature, then even if you take a fall, it's still okay. But in general, it turns out the new types of storage based on flash, they are much more convenient, but they're expensive, okay? For example, the camera, for example, it all uses this kind of memory only, okay? As far as to my knowledge, nobody has tried to put camera and a hard disk with it. There might be some models, but I'm not aware of it, okay? So basically, because if you think about it, it may be that especially if you have a video camera, for example, right? The disk will make some noise, okay, which will also be captured, will shake, okay? All these things are problems, so you don't want to incorporate this. So cameras usually never do that, but that's why they have solid state disk as the most important part, okay? And you notice that there are differences in the way these systems are used, okay? Camera, for example, most of the times you're writing songs, made a mistake. In camera, most likely you're putting big files, and these are usually megabytes, right? Multiple megabytes. So a system that is geared for camera, okay, ideally should have not a 4 kilobyte block sized system. It should be slightly bigger possibly. But what is the current situation? Because you want to be able to take the camera and put it into any PC, it has a fat file system, okay? So the fat file system essentially decides what the block size is, okay? So even though the camera should have a much bigger block size, why will that help you if you have a big block size? It turns out the metadata that you want to keep, right, is proportional to number of blocks, right? So if you have a very large block size, then essentially you're reducing the metadata by that factor. So you're going to reduce it by a factor of 1000 almost if you use a larger block size, okay? But it's not done because of interoperability reasons. Basically, your machines are what you have. If they are able to handle FAT 32 whatever, that's what you use, okay? So that's the reason why ideally you should design the storage for the specific application, but that often creates interoperability issues, okay? So you need to handle that part. Same thing about smartphone also, okay? Because if you think about a smartphone, nowadays you come with 8 GB, 16 GB, 32 GB kind of stuff, right? Now the usage pattern of the smartphone, what kind of thing could it be? You're updating, you are storing music, you're also updating your contacts, your if it is a smartphone, it also is doing lots of applications, right. So, what could be the right model for smartphone? So, it is almost looking like a regular desktop kind of system, right. So, because there could be variety of there could be varieties of applications, and it turns out smartphones do not have a disk on them. Okay. So, there is only 2 level storage, DRAM memory, and you have SSD memory, okay, the flash memory. Okay. So, the thing is that instead of the disk situation, you have SSD. Okay. So, you can see that there should be some difference with respect to how these are being used. Okay. Again, what is the kind of file system that the smartphone uses? Again, it has to be interoperable with, because you can take your smartphone and attach it to a PC. Okay. Again, it should have a way in which you can read those things, right. Again, most likely what will be the file system? It will most likely again a FAT32 file system, most likely. You can design things in a which is different manner, but that will make it non-interoperable. Okay. So, this interoperability is a big issue for consumer devices, very big issue. You have to handle it somehow. Okay. If you are not able to handle it, then nobody will touch it. Okay. So, that is why all these things are essentially mostly using FAT32, and it may or not be very good. Okay. For example, in these systems, there is not much serious attempt at reliability. Okay. Or for example, if there is a bit error somewhere, there is no way to recover from it, okay, because that kind of stuff has not been designed in. Okay. With laptops, I think things could be slightly different, because you store critical information. Of course, you store critical information in smartphones nowadays also, but still not as critical as what you probably might store in laptops. So, some laptops actually have let us say ability to recover from errors, but that is very minimal still, because for example, most laptop memories are not ECC. So, if memory itself is not ECC, there is no point in worrying about disk failures. Okay. Basically, what it means is that the memory itself can be introducing, let us say, errors in it. No point in trying to recover from it on the error memory itself, because that is the largest generator of information, because it is computing all kinds of things. It is a cache of all the important stuff, and part of it is going to come to disk. If that generated stuff itself is junk, okay, you do not worry too much about other things. Okay, and that is the reason why most laptops are. But in principle, one can imagine future generations where this laptop memories become very big. Okay. Nowadays, you can get laptop memories for about 4 GB, 8 GB, right? And if you go to 16 GB or etc., then people will start worrying about, given the large amount of memory, the possibility of error is now much higher. Okay. So, then probably most likely bigger in the future laptops with let us say 128 GB or such memories, they will incorporate things like error correcting codes, ECC. Okay. In that which case, then you start worrying about, yes, I have taken care of my memory, but what about my disk? Okay. Should I do something about that disk also? Suppose it is silently corrupting things, can I handle it? Okay. So, in those kind of situations, you might find that you may want to protect it also against certain errors. Okay. That is where what you might call as, there are some systems called RAID systems, RAID, R-A-I-D. Okay. What is RAID system? Let us just look at these RAID systems. So, we have something called RAID systems. What are these? This is that it is redundant array of inexpensive disks. So, there are varieties of RAID systems for reliability. The one which is most common is RAID 1. What you do is, suppose you have a disk that is called, symbol for disk is this typically. So, there is one block here, you have an exact copy here also. So, if there is any, if this particular disk fails, now the disk can fail in multiple ways. One way is what is called whole disk failure. Failure models, what is it? You can have failure models. One is whole disk. What does it mean? It means that somehow something has gone bad, so that nothing in the disk is readable. Okay. Essentially, something has happened to the ARM, something has happened to the electronics, the controller circuitry, that something is there, just not taking commands. Okay. So, the whole disk has failed. Okay. It's total loss. Or you can have what is called sector errors. Okay. Often called latent sector errors. Okay. Latent sector errors. Okay. What are sector errors? The whole disk has not failed, but parts of the disk have failed. I think some of you might be familiar if you had used floppies in the past. You will notice that some files are readable, some files are not readable, right. So, that means that most of electronics, most of the mechanical components are all working, but some small media, part of the media has failed, it has gone bad. Okay. So, it could be because of dust particle, it could be because of something, okay, something which caused that particular small section of the medium to go bad. Okay. Now, there is also another type of error called latent, this what I call latent sector error. That means that you are able to write to it and then you do not touch it, and then after about a month you try to go back to it. In that intervening period, it has gone bad. It was okay when you wrote it, okay, but it went bad after 1 month. This, in some sense, the sector failure is latent. It is somewhere there, but you can't predict when it is going to happen. So, if you have a latent sector error, you can lose the data. But suppose I have RAID 1, the idea is that if there is a latent sector error here, very unlikely it will have the same error this place here. Therefore, I can, if I am unable to read from here, I look at a corresponding area on the other disk and use it as a way to fix it. How do I fix it? I can't write to here again, because that part of it is gone. Okay. So, normally disks have what is called errorless, and they have a spare area also. They have something called errorless and spare area. Spare area. Okay. What does it mean? That in a disk, for example, you have some sectors, some tracks, okay, at the outside, for example, which are for these spare areas. So, there are some sectors out there. Okay. And when you try to recover from this error, which happened here, you want to take the copy and basically you remap it, so that this becomes this. So, basically what happens is that the hardware, the firmware of the system, of the disk, when somebody asks for this on this disk, it will have been remapped to this spare area. Okay. So, that the software does not know anything about it. Internally what has happened, you ask for the same place, but there is some table inside which basically says that these things are all bad, it hit one of those things. Basically, in some sense you might do an associative match. It says that this thing has, you ask for this block, I look up in my error list, if it hits there, then I know that you have to look up the corresponding place in the spare area. Okay. So, that way what happens is that you can recover from sector errors. So, the RAID 1 gives you the ability, but the problem with this is that you need to have 100% extra space. Okay. This is a problem with this solution. Okay. You can use what is called coding to reduce the amount. We will talk about it slightly later. Okay. So, what is one problem with this kind of solution? The problem with the solution is that normally I am expecting, you know, that the disks, they are good only when you are accessing things sequentially. So, what has happened right now, because of an error, you suddenly went to, you are thinking things are nearby, right, logically went from this block to this block, but this block actually is not here, it is actually somewhere else, and then you want to go to the next block. So, what has happened, you read this block here, go somewhere and again come back here next. Okay. So, this creates what you might call as sudden latency variations. Okay. Luckily not much, but if you are talking about video streams or audio streams, right, audio especially has serious problem, because audio is basically what is called a hard real time system. Okay. Audio, why is that? Because if you don't, because you need some samples every 20 milliseconds, you need a sample. If you don't get it, then you can hear a click or something. Okay, you can do some adjustments, but still typically in spite of your best efforts, oftentimes you hear a click. That click is basically the lack of information, because your system is not able to give that sample in time. Okay. Video is slightly better because there is a lot of redundancy. I think some of you might know that in video you have what are called predicted frames. You have something called I frames, B frames, and predicted frames. Okay, there is some redundancy in the system. So even if you drop some things, it's okay. So if you don't get the thing in time, you just drop it for the time being and continue surveying the next ones. Okay, that usually you can't really see it, or I also can sort of adjust to it. Okay, with audio it's a problem. Okay, so you'll notice that these kind of solutions work, but sometimes there can be some things. It could be because of problems like this. Okay, if you hear a click, I'm not saying it's because of this. Okay? It might be bad recording itself, but it could be because of some of these things also. Okay, so if you are thinking about laptops in the future, who knows? You might have RAID systems also coming in, and RAID 1 is an expensive way. It can be done. It is simple, and there are better ways, more cheaper ways. For example, RAID 5. Okay. So RAID 5 is often used. There is also something called RAID 6, which is even more, it's better, but it is more complex. In RAID 5, what happens is that you don't want to pay 100% cost. What you do is, you have a disk, you have so many disks. You can have, for example, 8 disks, for example. Okay, I'll just put, let's say there are 8 disks. What you do is, same block, you take these ones and do an XOR and store it here. Okay. So basically this is what's called the parity. This is the parity. So parity is XOR of, let's say, D1 to D8. Okay, let's say D7. Okay, because you have total 8 disks. Okay, so you have an XOR of these things, and if one of them fails, let's say D2 fails. Okay, you can reconstruct D2 by, let's call this parity. Okay, so D2 will be given by XOR of D1, D3 up till D7, come on. Okay, so this equation is valid. I think some of you, if you know the properties XOR, you can see it is very clear, because it turns out, what is this? You are XORing D1 with XOR of this one. So D1 and D1 will cancel off, and D7 will cancel off, and D3 also will cancel off, only D2 will remain. That is why you will get finally D2. Okay, because what is XOR of? XOR of A comma is what? Is 0. Okay, so basically you are cancelling. When you do XOR of these things with P, right, all the common things will fall off, only that is not there here is D2, that is something that will come out. Okay. But what is good about this? The good thing about this is that you have some efficiency here, because you are talking about, for 7 disks I have to have an extra disk. So your efficiency is about, you lose only one out of every 7, 1 out of 8 disks. Okay. Basically you are wasting it in some sense, because of redundancy. Okay. What is the problem with this thing? The problem is that if I want to recover from this, I have to go and read 7 disks. That will take a long time. In a sense, the recovery is slightly heavy. In the case of RAID 1, right, you look at RAID 1, there are only 2 things, you just have to look at other disk, you just have to read it. It's somewhat simpler. Okay. So that's why it turns out RAID 1 is most often used. RAID 5 is used only in extremely large capacity systems, okay, where this loss that is there in RAID 1, okay, is too intolerable. Okay. For example, you have some petabytes of data. Okay. I think as I mentioned, petabytes of data can be involve megawatts of power, right. So, if you are worried about power consumption, probably you may want to go to RAID 5. Okay. You have to be careful about this. Okay. Now, you can also have RAID 6, where instead of one parity disk, you have two parity disks, and they use some slightly more advanced techniques. They won't use XOR. They use something called Galois field arithmetic. Okay. RAID 6 uses this. This uses mostly XOR. Okay. So, this is a slightly more expensive method where people have used it. For example, many commercial systems use RAID 6, sometimes RAID 6. But what has happened now is that there are issues of reliability even with RAID 6. So, people have gone to the next step. For example, people at places like CERN, for example, even with RAID 6, they still have some amount of errors. So, they will want to go for things which have not just two parity disks, also another one, third parity disk, okay, triple parity, triple redundancy. Okay. Some people are starting to look into those things. Okay. Now, you notice that going to more does not necessarily mean things are okay, because you can have what are called errors during reconstruction itself. Okay. For example, you have a RAID 5, right? If I figured out that this thing failed, okay. So, this failed, so what did you start reading from there? As you are reading it from there, it discovers that you discover that this thing is unreadable. The disk has not failed, but this sector error is there on this particular thing. So, I really can't reconstruct the data. This is often called one and a half error. That is a full failure followed by a sector failure, okay, because you have to read that particular thing and somehow it was not there, okay, right. Sometimes it happens and people worry about this also. Especially if your data is very large, you have to worry about this. Okay. And the way you eliminate this problem is what is called scrubbing. Scrubbing. What is scrubbing? It's like you periodically check, is it readable? So, essentially instead of waiting for 1 month and discovering after 1 month that you could not read it, right, every day you go through the whole system, okay, in the background. In some sense, when the system is not very fully utilized, you keep reading it to ensure that you are able to read all the sectors. So, before that major error occurs, you are essentially keeping everything readable. Okay. It is just like some aspect of you be paranoid about data. Okay. Things can go anytime, things can fall apart anytime. So, what you do is every day you keep doing it. Okay. So, this is done, actually this is called data scrubbing and it is widely used in large systems. In very large systems, terabytes of stuff, you have to do it, there is no escape. Okay. So, you have let us see the kind of error mechanisms that you can see. If you think about it, you can see how many levels of things are there. On the disk itself, you have what is called Reed-Solomon codes, and these are geared for handling things like 40-bit codes for 512 bits, 512 bytes, sorry, 512 bytes. Okay. So, sorry, I think I should name 40 bytes for 512 bytes, sorry. This is the kind of extra information that is kept. Okay. So, the read column is there. What else do you need? You often have things like RAID 1 or 5 or 6. In addition to this, you have scrubbing. Okay. So, you do lots of these things, then there is some chance that it will actually be there when you want it. Okay. So, okay. So, I think I covered some of this part of it. Okay, so let's get back to. So when you go, see, we have the mobile storage. Suppose I am done with the mobile storage. Okay, I'm pretty sure you'll find storage in very different forms soon. Okay, and it will be everywhere. Just like computing is everywhere, you'll find storage also coming around. Okay, and I think mobile storage is the reason why you are starting to see lots of interesting gadgets. Okay, camera being the first one that you must have seen. Okay, and smartphones, laptops, all these things are somehow enabled because of mobile storage. Again, you can also have what's called personal storage, much bigger amounts of stuff on the PC, for example, or you may also build a home RAID system. What's home RAID system? You decide that nowadays in many homes you will have multiple laptops and at least one big desktop, and you will try to keep the big desktop as the place where you have a RAID system. So that will be the backup place, that will be the place where you keep another copy just in case your laptop gets stolen, lost, or whatever it is, right? So you can even build home RAID systems, and nowadays most of the chips that you get have support for RAID 5 or RAID 1. That is, you can put a controller which has support for RAID 1 or RAID 5, and therefore you can have multiple disks on the PC, and then you can have a low cost RAID system. But what is the good thing about this? The good thing is it's low cost and it doesn't change your model that much. But what is the bad thing? The bad thing about this is that if something happens to that disk, something happens to that PC. Why should something happen to the PC? There might be a flood. Okay, the whole PC is underwater. Okay, which is not something unusual. Okay, so in Bangalore also it happens. Okay, it happens many places. Okay, so you can have flood, you can have fire. Okay, fire is very common. You have a building, the fire takes place. Both the disks are there, they are doing all redundancy, everything. But what is the use of redundancy when the whole disk is fried? Okay, in a fire. Okay, two disks are all both together, because that's why you need to have home RAID systems are useful to some extent, but they're not good enough. Okay, if you're worried about data, that is where this new trend about what's called cloud storage, which are not written here, has also come. What do you do in that case? You not only store it locally, but you store a copy in the cloud also. Okay, so what is the reason why you want to go to the cloud? It is purely for disaster recovery. Okay, here the issue is that I can't keep everything in the cloud because cloud becomes, it is too slow, because normally I can be dealing with multiple gigabytes of data, accessing gigabytes of data through whatever current technologies we have is not exactly fast, it's actually quite slow. Okay, so because of that you can't really afford to keep everything on the cloud. I think some of you might have noticed that if you want to upload something like your all the pictures taken, right, it will take some time before you can upload it, right. So, and these things are not exactly huge, because you might at the most upload some 40 or so pictures or whatever, 40 into 4 megabytes, that's about, let us say, not 4 megabytes, okay, 10 megabytes also. I mean, 400 megabytes will take at least some amount of time, but you can even have much bigger sets. Okay, so cloud storage may not be that effective as regular access, so you might use it for recovering purposes. Okay, so so basically nowadays I think all of you are probably using it some form of that. Either or the other solution is that the cloud storage is part of the application itself. Like when using Gmail, that cloud storage is part of the application, so that you don't store it locally, it's always up somewhere out there, and the people who are giving that application service, that is their business to keep it intact. And they might use RAID systems or whatever system they might use RAID, they might use distributed storage models, etc. Okay, which we will discuss soon. Okay, so that's possible. So one is to just store the things. Other thing also, you may also have what is called a home NFS server. That is, your laptop, etc. They don't directly use the, they don't have storage that much on the disk. They directly use it from the home's NFS server. Okay, this also some model a lot of people are starting to use. Okay, and this can be helpful in many cases. Okay. The reason why that's good is because if I have multiple devices, I don't have to back it up, okay, each one of them individually. I back up this home NFS server and I know that everything is there. One of the biggest problems we have is that when you have multiple gadgets, you forget to back up one thing, or you don't back you back it up at different times. So there's always some let us say some incoherence about the data what you have. Okay, you don't know, you have to manually figure out what is the latest copy, etc., etc. Okay, but if you use this NFS server kind of model, you know that everything is as per what is the latest thing is sitting in NFS server, and since it's a single big system, you can afford to put RAID and other things, RAID and other redundancy models out here much better. You don't have to do it on every single small device you have. Okay, so this also is starting to become common, and okay. So similar to this home NFS server, at a department level and organizational, also you have storage of this kind, right? This is very common. I think, for example, you're in the department, you are using NFS server, right? And NFS is the Unix based model. There is a Windows based model called CIFS that also widely people use. Okay, so now the difference here is that, as I mentioned, before, up to this point it was all local to this. It was basically local to the system, basically direct attached storage most of the times, all this while here. And from here onwards, you are starting to see some kind of networking also in the picture. Okay, so home NFS server and NFS servers at departmental level, organization storage, for example, these things all depend on networks. Okay, now you can access these things through Ethernet or through wireless, especially if you like home NFS servers, right? Most likely you are accessing it through wireless, you are not accessing it through Ethernet. Now there are some issues here also, because it turns out if you use NFS servers, typical NFS servers have what is called 8 kilobytes as the block size. Okay, now 8 kilobytes is a slightly big packet for wireless. Why is that? We can start thinking about that this way. Okay, if you look at what is the bit error rate of some packet, suppose I have let us say k bits, right. So what is the, suppose there is a bit error rate of p, this is what is called bit error rate. Okay, now that means that any bit has a probability of being bad with p, okay, p probability. The question is, if I send k bits, what is the probability that the packet is damaged somewhere? Okay, so it turns out you can easily analyze this. So what is the probability of so if you look at this, right, this is the probability that this is correct is 1 minus p, right. This also is 1 minus p, right. So if you have k bits, the probability of everything being correct is 1 minus p to the power of p. The probability the thing is bad is this, right. The packet is damaged in some way. Okay, packet is bad, right. So now if you think about it, even if p is very small, okay, let us say p is, luckily for us, p is 10 to the power of minus 15 for disk. So if you do this, 1 minus 1 by 10 to the power of 15 to the power of, let us say k is 8 kilobytes. How many 8 kilobytes? 8 into 8 bits into 8000. How much is 64,000 bits? 64,000. Now we have a rule saying, we have a approximation 1 by k is what is it? Approximately equal to 1 minus ak. So this is how much? It turns out to be very small. It is 1 minus approximately 10 to the power of minus, sorry, I made a mistake here. Okay, what is the, this one is what? This is 1 minus 10 to the power of approximately, you can make it also as 10 to the power of 5. Okay, this is 10 to the power of minus 10. So the probability that a packet is bad is 10 to the power of minus 10. That is very small. Okay, with the case of disk, it's really small. Now suppose in the wireless case, what happens? In the wireless case, you know that the wireless is a bad medium. Okay, what does that mean? It's a bad medium. You notice that the signal keeps changing all over the time. You go here, suddenly you can get something. You go somewhere else, you can't even get the signal. The bit error rates are much higher. They're as much as 10 to the power of, who knows, minus 5, minus 4, depending on the situation. Okay, minus 8, things like that. Okay, it is highly variable. Okay, that means that if I send a packet and it's 8K packet, what will happen? You use the same formula again. So you will see that at a particular rate, right? Especially again, we'll take the approximation 1 minus AK. At of course, so if this will be almost 0 when K is equal to 1 by A, right? I'm sorry, I used P here and K here. Let's make it P here again. Okay, so let's call it P here. Okay, P. Okay. So if it is 10 to the power minus 5 with 10 to the power 5 bits, there is definitely bound to be an error. And here talking about 64,000 bits. That means that packet, even if sent, most likely will be dead. A good chance, because the probability is so high. Okay, that means that if you think about NFS, which sends it in 8K byte chunks, okay, it's not a well suited protocol for this kind of systems. Okay, so that's something you have to worry about. You have to, it's true that you can always use it, but you have to be aware that wireless is a different medium. So if you're building your home NFS, right? Sorry, okay, you may have to change the protocols a bit. Okay, you may not have to have 8K write sizes. Okay, you might need to do it small. Luckily for us, the issue is that you are going to send that, you can't send 8K as such in a wireless packet. Okay, you send it 1500 bytes at a time. But the problem is you send 1500, 1500, 1500, 1500, but there could be, because you are essentially talking about ability to send so many of them intact. Only then the stuff is got on the server side and it actually writes it. If any one of them falls apart, okay, then you are dead. Okay. So again, it has to be retransmitted. So to reduce the retransmission rate, you have to figure out a way in which you can reduce the size of the NFS packet. Okay, that means that instead of NFS, which standard size 8K, you should start writing in smaller size. Probably, who knows, 500 bytes, 700 bytes, things of that kind. So there is, you send in one single packet, and the chances of your error is not, let's say, almost 1, but it's close to 1 in 10 to the power of 3 or 1 in 10 to the power of 2. That is still manageable. Okay. So that's one of the things that you should remember, that everything in a system, when you think about it carefully, things are all varying depending on the technology parameters. You have to be very careful that you choose the right parameters, and if you put some technology in a new setting, you have to start thinking about what was the way it was, what was it designed for. I am using it in a different context. Am I violating those design assumptions? Okay. If I am violating it, most likely you have to again redo the thing. Okay. There is no way to get it right. Okay. So that's something which I want you to be clear about. Okay. Now, so again, if you look at all this stuff, you will find that, as I mentioned, I used wireless here. It's a bad thing for it. But if you go to departmental organization setup, what do you have? You have either nowadays gigabit Ethernet, sometime in the past 100 megabit per second, even earlier 10 megabit per second. At 10 megabit per second, NFS was very bad. It was not very nice. 100 megabit, it is reasonably good. Gigabit is quite good, and you can, people are going to move to higher speed, but 1 gigabit is quite good. Okay, you can essentially do some very good. Essentially, network is no longer a bottleneck with 1 gigabit. Okay, so there are issues here also. Basically, when there are NFS has some timeouts. So, if you write something and somehow it does not make it to the other side, it waits for 5 minutes or 3 minutes, okay, and then again retransmits it. So, in a sense what happens is that your timeouts are sufficiently large because the medium is, especially gigabit Ethernet, etc., they're very good. We are talking about wired medium, we are not talking about wireless medium. Okay. If you are using wired medium, you can keep timeouts to be substantial. You can keep it for 2 minutes, 3 minutes, etc. Whereas if you have a slight, if you are doing gigabit Ethernet wireless, which also is going to come soon, okay, then you might want to keep the NFS parameters slightly smaller, because the chance of error are high. Therefore, you should be able to respond to it a bit fast. You can't keep waiting for it. Okay, if you wait for 3 minutes, in the 3 minutes you could have sent so much, right? So, you should detect errors earlier, and therefore, you should, if you find some error, you should ask it to retransmit a bit earlier, not wait for 3 minutes. Okay, that's a bit lost. So, there are some issues of that kind that you have to work around. Okay. Again, here also, again, you will notice that you will start changing with respect to the kinds of technology you use. I mentioned here home NFS server, you are going to use things like wireless medium, okay, most likely, because wiring is a big issue. You don't want to do all those things. Whereas here, most likely you are in an organization where everything is wired. Okay. Now, since it is wired, you can have different types of cables here. Okay. You will be using what is called, typically if you use gigabit Ethernet, you will be using what is called some fiber. Okay. Or basically there are, you can, in the past it used to be what is called coaxial cable, and basically use the principle of total internal reflection, so that it is essentially no attenuation. Okay, that's how it was used in the past. Now, fiber actually does something. Coaxial cable is basically very good for transmitting electromagnetic waves, and now it has come to fiber optics. Okay, fiber what is called optical fiber, and if you use optical fiber, essentially you transmit also using total internal reflection, so that you can drive bits, okay, using optical waveforms. You can do it with very low error, but there is a problem here. What is the problem? The problem is that you have to convert from electrical signals to optical signals. Okay, somebody has to do that. Okay, so normally what happens is that in low cost systems, since things are nearby, you don't want to take the trouble of doing it using the conversion from electrical to optical and vice versa. It's too costly. Okay. So, usually what you do, you what is called gigabit on copper, that is, you still do it using wires only. So, right now 100 megabit etc. goes on copper. Okay. All what we have, everything what we have goes on copper. That means it's a regular copper. If you look at the cable, right, there are multiple lines, and one of them, the conducting thing, is copper. Okay. So, in gigabit also, as long as the distance are not too long, you can use copper, and that is usually a low cost solution. That means you don't have to have conversions. Whereas, if you are going to large scale organization storage, the distances can be substantial. Now, it turns out you can't really drive the signals well on long copper. It's not possible. Okay. So, and why is it needed? Because if it's an organization system, you need to worry about availability of the system. That means that you're no longer happy with just RAID systems. That means that you need to also have a system which, if the local storage falls apart, fire or whatever, right, a copy is sitting there at least some kilometers away, so that if the fire happens here, very unlikely a fire will happen there also, right, separated by 10 kilometers, 30 kilometers, 50 kilometers, some far away. You want to keep this, okay, storage. Okay. So, if you use that kind of model, right, then you can't use copper for it. Okay. What do you have to use? You have to use a fiber optic cable. That means that you need to be able to translate from electrical signaling to optical signaling to transmit it. Okay. So these things become slightly costly. Okay. So the various ways to convert it. The standard thing is something called SFPs, okay, and they add cost to it, but it turns out all high-end storage, especially if it has to be driven some distance, has to use optical means only. Okay. So this is something very critical for disaster recovery. Okay. I think you might have heard about some hurricanes and this and that, which essentially wipes out things within a space of about few kilometers. So you have to keep it at least across some, if not hundreds of kilometers, 50 kilometers at least, you have to keep it. Okay? Then only there is some chance that you can. If you have a big weather-related phenomenon, right? Suppose you have a Mumbai downpour in 2005, I think, right? It dropped something like 910 millimeters in 24 hours, right? Something like that, right? Some of you might remember this. It means whole of Mumbai is flooded, okay? There is no escape. So you cannot just keep a local copy in Mumbai, you have to keep it somewhere else, okay? So for that you need this optical transmission, okay? Because that is only. But there is a problem there also. Let us just quickly look at what the problem is. So you have a copy here, right? Let us say you are a bank, okay? You keep some piece of information here, it is a local copy, you keep another local copy, okay? Let us call it L, L1, L2, there are two local copies. This is in a single city. And then for disaster recovery, you keep a copy L3, which is some for this. For example, this could be Mumbai, and this could be Chennai, okay? That means that any transactions you do, you want to make the transaction, the results of it available L1, L2, and this, let us call it remote R, okay? Should be L1, L2 R. But you notice that if you want to keep everything consistent, then this takes a long time. It can take tens or hundreds of milliseconds. If it takes hundreds of milliseconds, that means that you can at the most do 10 transactions per second, which is too low, okay? Whereas you can probably do some thousands of transactions here, because the things are in the same city. So that is why you need to have different models, and the model that often people use is called, you do it transactions here synchronously, okay, and you do this what is called asynchronously, okay. That means that here when you do the transaction, you do it here and do it here and wait for the confirmation from both sides, only then you say the transaction is committed. Whereas here you do it asynchronously, you send it, do not wait for it, and you try to come up with a model by which you can, in case something happens, some failure occurs, there is a way to fix it up based on copies here, okay, you figure out what to do, because this one is going on synchronously, okay. So only this can, if it fails, right, you may have to do something about it. You sent it, it did not somehow write it, that means you have to figure out what happened here and re-apply it here, okay. In a sense, this is going to be strictly like a backup situation, okay. So, so various models like this are done, and this idea about synchrony and asynchrony is very common. I think even in the case of many systems, okay, many disk operations are not synchronous. In synchronous, what happens to disk operation? I do a synchronous write means I write to the disk and I will wait for the disk to say I finished writing it. That is synchronous, okay. Disks also have asynchronous mode. You just initiate the request, okay, say please write, but do not wait, you proceed immediately, asynchronous. There is also one more model which is called delayed writes. The thing is, you do not even queue it, you just keep it in memory. Here at least you went to the disk and said write it, but I am not waiting for it. Here what you are going to say is that I know disk is too slow, it is 10 to the power of 4 times or 10 to the power of 5 times slow, okay. So I don't want to even go to disk. I'll keep it in memory. I take my chances. Okay. So in case something happens, I will have some way to recover from that situation. So I lose some stuff in memory, and I will make sure that I keep some checkpointing information, so that even if something bad happens, I am able to recover from it. Okay. So these things are commonly used in file systems: synchronous writes, asynchronous writes, and delayed writes. Typically, delayed writes are used for data in file systems. Synchronous ones are usually for metadata, typically. Okay. And asynchronous in many situations for both metadata as well as for data. It depends. Okay. If you look at a database, they are not comfortable with these two models. They usually do synchronous, because usually you are dealing with money. A database means usually your bank account, all this kind of stuff. You can't afford to lose the data. So usually the data there is typically, because in a database, data is more important than how the system stores the information, right? The metadata for where it has stored it. So data has to be stored synchronously. So database have a different model. Okay. And so there are issues of this kind, latency issues, that are very critical in the design of the systems. So you will start noticing these things once you start looking at more closely. Okay. So that is that part. You can also have what is called highly available storage. Okay. Again, when you're talking about large scale storage, this NFS SIP server, they usually can handle some amount of let us say availability, but you might want to design specially some designs which are highly available, like I just mentioned about this bank system, right? You want to keep it at multiple copies, but this highly available storage actually tries to do it at every single level. Okay. So what we did previously was a slightly simpler model, right? So we are talking very abstractly about copies of data, but in practice it can be something more, let us say you need to take a much more detailed look, okay? Because when you talk about a failure, you are not talking about a system failure as a whole, as a system. There may be multiple parts to it. The question is, you have to look at each part and decide what to do with it. Okay. For example, you might have two servers, and then the server has what is called a HBA, is a server S1, S2, HBA. As I mentioned earlier, what is HBA? Host bus adapter, essentially an agent of CPU to access a disk, right? It's an agent, okay? S1 HBA, and then it talks to data. Now, what are the situations possible now? The server can fail, HBA can fail, the disk can fail, right? So what is the solution to this? In case the server goes away and this data is only accessible as S1, then it's a problem, right? That means that until the server comes, I can't use the data, but the data is available, nothing has happened to it. So the question is it possible for me to, even if S1 fails, can I access the data? The way you do it is by probably providing one connection like this. Okay. What does that mean? It means that even if this is dead, this HBA is working, this HBA is working, these two are working. So this S2, for example, is still alive. It can use the HBA if it is what is called dual ported HBA. Dual ported HBA. What it means is that it has connections to both this data. Okay. Basically, what we are talking about is so there is a disk out here. Okay. Basically, I put RAID 1 here. Let us say, to make it simple, RAID 1. Okay. So there is two pieces of data here. Okay. So the idea is that if this fails, I still can, S2 can access this path and get to this data. Okay. So, of course, if it is the case that this red one, then a copy is also sitting here. So, I can actually access like this itself. But suppose it is not red one, okay, there are different pieces of data here. Then I have a situation where S1 fails, S2 can actually go and get this data, because there is no copy of it here. If it is what is called RAID 0. What is RAID 0? It is basically concatenation. Okay, you have some huge piece of data, let us say 4 terabyte, it is 16 terabyte, let us say. Now, the maximum biggest size disk is 4 terabytes currently. You can't put 16 terabytes in 4 terabytes, so you have to join them. So, you basically this is RAID 0. That is basically what you get is you get a 16 terabyte disk which looks like a single disk. That is RAID 0. Okay. So, if it is RAID 0, that means this data and this data there is no commonality. So, if something happens here, unless you have this path, there is no way to access the data. Okay. So, now there are 2 ports, one port to this data and one port to this data. Similarly, HBA also can fail, this also can fail, right. That means that you need to have okay, you might have dual ported systems here. Okay. So, you will find that there are multiple paths around, so that in case there is either a failure at server, HBA or data, okay, you can survive those things. Okay. This is what is called a highly available storage. Okay. And I think I already discussed previously about web scale storage. The Google file system was a good example. I have not discussed parallel storage, which I will cover a bit later. So, I just wanted to give you a high level introduction to this stuff. Now, we will dive into each of these things more systematically. Okay. We will start looking at this NFS and those kind of systems, and then we will look at how to get these things like one by one, high level storage, parallel storage and web scale. Okay. Thank you.